Welcome to Transmission Lines in Chapter 10. Chapter 10 of the book Engineering Electromagnetics by Hayton Buck, 8th edition, McGraw-Hill. We've received permission to reproduce figures and equations from the book, so when I refer to those, I will either refer to the figure explicitly as in the book, or write the equation as HB and then the equation number so you can follow exactly from your textbook. So let's begin with a picture of a model of transmission lines, and that is shown in figure 10.1. In figure 10.1, you can see a battery with voltage V0 connected to two lines, top line and bottom line, and switch S1 has just been closed. What actually happens? Well, if you look at the figure, you can see that something's happening in blue. And in the text, they say the line's getting charged up. So exactly what does that mean? Well, the blue represents a moving wave in the line. It's launched at the time which the voltage is switched on. So when the voltage is switched, at the point of switching, it goes from 0 to some V0 volts. That is not DC, it's a transient. It has frequency, and it's that transient that launches the wave. So behind the wave in blue, everything's happening and the line is getting, as they say, charged up. To the right, all in black, the wavefront, as indicated by the dotted line, has not yet moved. It is moving. It will be a wave, for example, to the right, which we know from previous work is of the form f of x minus vt. That's why we worked so hard to get that f of x minus vt. Here's a question for you, and we'll answer it in class. Why don't we worry about this anytime we're doing circuits in the lab? You know, we have some circuit exercises, we have the oscilloscope, we're measuring in kilohertz. Do we have to worry about waves? So that's something to think about, and I want to put it in the right framework by saying it all has to do with frequency and wavelength. And I want you to calculate the wavelength associated with the speed of light. So that's 3 times 10 to the 8th meters per second. And the frequency of, say, a typical lab frequency when you're doing test measurements on the oscilloscope, say 100 kilohertz, which is rather high. So what's the wavelength at 100 kilohertz? And then think about that wavelength relative to the size of the circuit that you're building. And that's the key point here in why we may or may not have to worry about waves. And we'll come back to that in class when we discuss it. Now, we have this picture of the transmission line. We want to model it mathematically. So now let's move to a detailed circuit description of the line as shown in figure 10.3, the next figure. Looks a little complicated, but I think you can see there's a little V here, and that's the voltage across the line. I didn't quite circle it, but that's okay. And you can see that that launches a current, and we model the line in the way described where we have a little resistance per unit length. So the resistance is R delta Z. A half is given for symmetry. Then we have a little bit of line inductance. So inductance per unit length times delta Z. And then we have a node here, and then the other half. So it's symmetrized in terms of description. So what we can think of is we have a voltage at this side across the terminal ends, and at the other side the voltage across is V plus delta V. We also have here as a model, and this is the new part, this shunt current from the node. So there's current that goes across the line. And that's something that we don't normally think of in a circuit. This is the wave part. This is the Maxwell equation modeling in terms of this circuit element. And since the current I over here is getting diverted at this node across, that's a model for the coupling between the top and bottom of the line, plus minus, the current at the other end is I plus delta I. So at one end of the line, we have a V across the line. As it goes through that little circuit element that I've described, we have V plus delta V. Current is diverted at the nodes, so we have entering current on the left, and on the right, we have a different current, I plus delta I. So we have two things to do to get the equations involved. These are circuit equations, so we all are comfortable with circuits. And the first thing we're going to do is apply KVL, Kirchhoff voltage law, to the dashed line, that loop. And that's going to be a class exercise. And when we do it, we'll get something that looks like this. Di V di Z is equal to minus IR plus L partial di dt. So you can kind of get that intuitively from looking at the line itself here. These are kind of the drops across the line for a small delta Z. An IR drop and an LDI dt drop and a reduction in the voltage. So that's the first thing we do, and that's going to be a class exercise. In class, you're going to do the exercise with the KVL around the dashed line. Now, that's one equation, and now we have to do KCL, Kirchhoff current law, and you can see the current splits. The node is labeled KCL, so the current's coming in and splitting. It's shunted across and going through. So that's KCL, and when you do KCL, we get an equation of this form. di dz is equal to minus. Now every time you see an I, it's going to become a V, and the R is replaced by the conductance, the shunt conductance, GV plus C dV by dt, and I'm running into the picture. Those are the two equations. So in class, and this 0, of course, is not part of the deal. That's my previous annotation of the previous slide. One of the dangers, of course, in doing a whiteboard is you have to be aware of that. So now we have these two equations, which we are going to do in class. And we will want to solve these. But you can see something interesting, that these are first derivative equations. And in the next video, I'll start to take it apart. And we'll look at simpler examples, and the solutions and the interpretations of the solutions are things that we've already looked at in quite a bit of detail in our previous work. Here are the last two equations that we just did, and I'm rewriting them to emphasize the reference to the textbook. Haight and Buck, Engineering Electromagnetics 8th edition, and these are equations 5 and 8 from chapter 10 that we are currently looking at.